Hello everyone, my name is Elhaji Amadou Diallo and I'm a PhD student at Waseda University, Tokyo, Japan. I'm going to present my research which is about learning coordination in multi-agent with decentralized POMDP. The outline gonna be as follows. First, we're gonna be having a very short introduction, then talk about the background, then the methods used in this experiment, finally the resultant conclusion. Multi-agent deep reinforcement learning is the learning technique of many agents trying to maximize a common expected reward. Generally, these agents are in a Markov game environment, sometimes non-Markovian environment whose underlying transition and reward are quite noisy and unknown. In deep multi-agent reinforcement learning techniques, generally agents use a stock of neural nets, mostly convolutional neural net, to approximate the action values. However, decision making in this kind of environment is a bit challenging since the appropriate behavior of one agent is influenced by the others, and the goal can only be reached if most of the agent, if not all of them, work together while avoiding the self-interested one to ruin the global task for the whole team. Our contribution here are many aspects. First, we're interested to know what will happen when we have a large number of agents. I mean, will the network converge? Will agents of the same team be able to learn some cooperative and the coordinated strategies and how they're going to do it? How much cooperation is required? The goal of this specific research is to give some answer to the previous questions. As a background, Duquesne is a very famous technique which tries to maximize a cumulative reward by estimating the Q values, and it uses a stock of neural network as a parameterized value function estimator by minimizing just a loss function. Generally, any kind of loss function is okay. Mostly people use a convex loss function. In this case, we decided to use the Huber loss function, which is which sum the advantage of having the mean absolute error and the MSE when the error is very large. However, the traditional Duquesne and mainly Q-learning algorithms always or often overestimate the Q-value due to the use of the max function when we update the Q-value. One solution was proposed is to have a double update, which consists of using two independent value functions that are randomly updated. Use one to update the Q value or to estimate the target. However, in many reinforcement learning problems, we don't need to estimate the action value for each actions, as some of them have little to no value to a given state. GLN networks decompose the Q network into an advantage stream and a value stream. Then we use this equation to put them together, aggregate the advantage value and the action value to constitute the Q values. We then use the naive epsilon greedy to balance between exploration and exploitation. This is important because in reinforcement learning, you don't want your agent to always act greedily. You want them to get exposure to unseen environment or to unseen states, then it's often useful to let them take random actions where they can learn some new strategies. However, you don't want to overdo it because if they explore a lot, that means they're going to be learning quite random strategy and you might take the risk to end up having a useless strategy. Then finding the right balance between exploration and exploitation is quite important. We model our environment as a decentralized POMDP, which is kind of similar to a POMDP. A POMDP is an environment which tries to mimic the Markov decision process while having like local observation. I mean, environment in which agent don't have the whole state and cannot model the whole state. The main difference between a decentralized POMDP and the uh, POMDP is the way agents learn their actions and the way they take it. In decentralized POMDP, agent might have a centralized learning techniques. However, the execution is decentralized. We propose this framework for training a large number of agents, and we believe that this framework can help us train agents. The framework is simply stacking a way of stacking the local view of each agent with their ID, because each agent has an individual ID for the whole training. We stock it and we feed it to the Q network, which use the target network to estimate the target value, and we store these experiences to the replay memory. Our environment is a battle environment in which we have two teams of an agent trying to fight against each other, and the an episode lasts for 1,000 steps. After every 1,000 steps, we see the winner of this game. The reward is as follows. The key idea in this reward scheme is here the reward of each team is just the sum of the individual reward of each agent. Because we're dealing with partially observable environment, it's quite interesting to see how the local view of an agent affects the global strategies. Here we propose this way of extracting the local view of agent and then stacking them to constitute a 3D tensor observation of a team at time step t. If an agent is dead during the battle, we replace its local view with a unique matrix which contains only ones. The network architecture for Dukan and double Dukan is as follows. We stock the local view of each agent at time step t, and we use the history from time step t minus 1. We combine it with the previous action taken at time t minus 1, and that's constitute mainly the input or the state at a given time steps. This tries to quite mimic the way decentralized POMDP reuse the history for planning problems, and the output is the key value for each agent. We should mention that the output here is related to a specific agent. After training, we use the ID to activate the weight of this network for a given agent. Then the network is going to output only the key value of a specific ID. That ID is the ID of an agent. The dealing network architecture follows the same as the Dukan and WDukan. The difference is here, after having few layers, we try to split the weights into an advantage in the value stream before concatenating them to constitute the Q values. And our loss function, which with Huber loss function, is uh, minimized by using a slightly variant or slightly modified version of Adam optimizer, and we not replaying randomly the experiences from the memory, but we use the prioritized experience replay uh, sample the experiences with higher priority for the target network. This is the result of 50 experiments with different random seeds. We train the agents and then we use the learn weights to test this agent against a Dukan baseline. And we can see from this figure the average result for Jalen double Dukan is always higher than the average result for double Dukan and Jalen double Dukan. And the key idea here is all techniques implementing the double update are the best because they try to converge to the right key value. Even sometimes they not quite converging to the right curve value, but they are very close to the right curve values. Despite the fact that dealing double duking, the orange one, has the highest reward in this setting, it also takes less steps to finish the games. Here we can see dealing double duking network takes fewer steps compared to the others. This is quite good because uh, from this we can be saying that GLW network seems to be the best in this case because it achieved the highest reward and it also do it in a very short time, as you can see from this figure. This table just summarize the metrics we use to compare them, and by each team, still it shows if we have dueling, the dueling WDQN network is always better no matter what the number of agent is. And our agent could learn some interesting strategies from nature probably. As we can see in this figure, like the green one is the dueling WDQN network and the orange one is a Dukian network. We see the green agent learn like in order to kill all the opponents, it's better to encircle them before killing them. That's quite interesting strategies they learn by themselves, and we have many variants of this kind of strategies. If you really are interested seeing different strategy, I highly recommend you to watch some videos from this link here. And we finally have the kernel density estimation of the visitation state. This shows the probability of a team visiting a specific area of the environment, and we see generally from the beginning to the end, a team often visit the whole environment trying to find if there are still some alive agents, some alive opponent, and trying to kill them. As a conclusion, we demonstrated that multi-agent can really converge in non-stationary environment and in adversarial environment, which is quite important because there are a lot of noise in this environment. It's quite complicated to learn any useful strategies from them. We've also shown some details about how our agent adapt their behavior, how they learn it, and also we've shown that even though our agent have only their local view, a very narrow local view, they can use it to learn some very complex global behavior. Thank you for your attention.